Robot teleoperation is an important tool for both robotics experts and inexperienced users. However, most teleoperation methods are too complex or inaccessible to one or both populations. In general, these methods are unintuitive, hardware-intensive, or require complex pose retargeting processes. In this work, we set out to design an augmented reality-based teleoperation system that is simple, intuitive, and accessible to both expert and novice users. Developed on the Microsoft HoloLens 2, the system leverages the device's hand tracking and voice recognition capabilities, enabling users to control a virtual robot gripper and, in turn, the physical robot through gestures and voice commands. The virtual gripper controlled by the user is a visual representation of the desired and effector pose for the real robot, which continually plans its motion accordingly. The user can control the gripper on the real robot by saying open or close, using a double-tap hand gesture, or by clicking on virtual button displayed in the button application. To reduce the amount of occlusion due to the hologram, the virtual gripper does not close along with the physical one, so that the user can have a better view of the object they are manipulating. To validate the effectiveness of the AR interface, we recruited 15 participants to take part in a user study. We asked each participant to perform 4 different tasks to test out the interface. The pour task consisted of carefully pouring ping pong balls into a bowl. The peg and hold task consisted of placing a cube into a slot in a tic-tac-toe board. The ring on peg task consisted of placing a paper towel roll onto a holder, and the bookshelf task consisted of placing a book-like object onto a makeshift shelf. We benchmarked the AR interface against 2 methods: kinesthetic teaching, assumed to be the most intuitive method, and the SpaceMouse, a common device for teleoperation and robotics. The objective metrics recorded in the study were the completion times, number of attempts, and the success rates. As expected, the results show that the kinesthetic approach is the quickest, most efficient, and most successful method, with the SpaceMouse following in most tasks. However, the AR interface outperformed the SpaceMouse in one key scenario. Many participants struggled with the SpaceMouse to easily reorient the gripper to grasp the paper towel roll, the only object that cannot be picked up with a top-down grasp. However, with the AR interface, the reorientation was seamless, and the participants spent significantly less time grasping and transporting the paper towel. In addition to objective metrics, we solicited feedback on the usability of the system using the System Usability Scale, the task load of the system using the NASA Task Load Index, and we also asked how likely they would recommend each method to others. The results showed that the kinesthetic method was the most usable and led to the lowest average task load score. However, the participants were most likely to recommend the AR interface out of all the methods. Furthermore, the AR interface received a slightly better score in task load and a considerable advantage in usability. In addition to the feedback from the questionnaires, participants were quick to underscore the intuitiveness, flexibility, and low-effort nature of the proposed system,